So today we will be talking about the Archimedean property. So this is 2.4.3 and all the Archimedean property. Okay, so what does this property state? Actually, write down a statement. So if x is a real number, then there exists a natural number, say n of x, so that x is less than that natural number. Now, this might seem obvious, right? It might seem that if you look at the real number line and you just see that the naturals keep on getting bigger and bigger and bigger, that there is no largest natural number. I mean, they just keep on going forever. But this statement here is stating this formally. If you think about what it's saying, you just take any real number, there's always a natural number bigger than it. That's another way of saying that there is no largest natural number. So we should prove this, and we're going to prove this using ideas from supremum and minimums. Okay, so let's look at the proof. So let's say let x be some arbitrary real number. And we're going to suppose to the contrary that this doesn't hold. So we're proving by way of contradiction. So let x be an R. And maybe supposing to the contrary, we're going to assume that x is larger than every natural number. So let x be a real number. Supposing to the contrary, assume say n is less than or equal to x for all natural numbers n. Okay, and we're going to see that this is going to give us a problem. So, okay. So what we can say is, that we have some set of natural numbers, it's non-empty, right? And it's bounded above. So the completeness property of the reals says that this set of naturals has a supremum if it's bounded above and non-empty, right? So I'll write that out. So the completeness property R implies that the non-empty set of natural numbers has a supremum since it's bounded above. Okay. Right, so let's go ahead and introduce the notation. Let's just say U is equal to the supremum of the naturals. And so again, what are we doing? We want to show that if we pick an arbitrary real number, there is a natural number larger than that real number. So in our proof, we pick an arbitrary real number and we're going to proceed by way of contradiction and suppose that that arbitrary real number is larger than every natural number, which means that the set of natural numbers is non-empty and bounded above. And the completeness property of R implies that that set has a supremum. When we say that supremum is U. Okay. So then by the definition of the supremum, so then by the definition of the supremum, since U is the supremum of the set of natural numbers, U minus 1 is no longer an upper bound of the natural numbers. So then by the definition of the supremum, observe that U minus 1 is not an upper bound for the naturals. Okay. So if it's not an upper bound for the naturals, then there is some natural number that's larger than U minus 1. So maybe therefore, there is some natural number called M with U minus 1 being strictly less than M. Right? Since U is the supremum of the naturals, subtracting any number from that supremum is not going to be an upper bound for the set of naturals anymore. So that means that there is some natural number M that's larger than if you subtract 1 off of U. But this implies that U is strictly less than M plus 1. Okay. This is a contradiction then. Why so? This is a contradiction since a natural number plus 1 is a natural number. And if U is the supremum of the natural numbers, then it better be greater than or equal to every natural number. But we just see here that this natural number is strictly greater than the supremum of the naturals. That's the contradiction. Done. So you pick any arbitrary real number, there's always a natural number larger than that real number. That's what this shows. And it's a direct application of the definition of the supremum, right? Together with the completeness property of R. So again, this is going to pop up quite a bit. The completeness property of the real numbers implies that any non-empty set that's bounded above has a supremum, right? So if we assume to the contrary that the natural numbers are bounded above by some real number, the completeness property implies that it has a supremum, which, as this short little algebraic line here gives us a contradiction. So there is no largest natural number, and that is the Archimedean property. Okay, so now let's look at some nice corollaries of the Archimedean property. There's several of them. That the following corollaries are sometimes referred to as the Archimedean properties of R. Okay, so this is 2.4.4 corollary. So if S is equal to the set of all 1 over n, such that n is a natural number, okay, then the infimum of S is equal to 0. So the set of all 1 over n, since n is a natural number, take the infimum of this, it's going to be 0. Another way of thinking about this is what is the limit, well, sort of, from like a calculus course, you would think of this as, what is the limit as n goes to infinity of 1 over n? It happens to be the infimum of that set, which is 0. So let's prove it. Okay, so first we need to like establish that indeed it does have an infimum, which is pretty easy because so since maybe that set S is not empty and bounded below by 0, S has an infimum. And we're going to call that maybe W. So I'm going to say W. Okay. And again, this is just another way of stating the completeness property of the real numbers. If we have a set that's bounded below and non-empty set that's bounded below, then it has an infimum. That's the completeness property. Okay. So, and then note that since 0 is a lower bound on the set S, then W is the greatest lower bound. So we're going to notice or note that, say, W is greater than or equal to 0. That's just by definition of the infimum. Okay. So next, maybe let epsilon be some real number greater than 0. Okay. And observe that, so the Archimedean property says if we have some real number x, then there is a natural number that's larger than it, right? So that's 2.43. So 2.4.3 implies so there exists some natural number n so that say maybe 0 less than or equal to W, which is strictly less than, or not strictly, less than or equal to 1 over N, which is less than epsilon. So why does that imply, why does 2.3 imply this piece right here? We already knew that, but where does that come from? Well, you can think of epsilon as being some small ratio, right? Some small real number. So there is, if it's a ratio, like you think of it like maybe this. So like that's some real number, right? 1 over epsilon. So the Archimedean property 2.4.3 implies there exists a natural number that's greater than that. And then you divide both sides by N and multiply by epsilon, and you get this right here. And I'll call this equation here, I'll call that equation 1, or inequality 1. Okay. So then we can say since 1 holds for any choice of epsilon, it must be the case that so here we can conclude that W is equal to 0. So why is that? Well, in a previous lecture, we showed that if a number, say W in this case, is greater than or equal to 0 and strictly less than epsilon for all epsilon, then W must equal 0. That was from a previous lecture. And you can prove that by contradiction if you don't have it next to you. But W is the infimum of that set, so that concludes the proof of this corollary. Okay. So give you a moment to look at that. And then now I'm going to pause the video and wipe down my boards. Okay, so let's continue with our proofs of these Archimedean properties. So what is the next one? So this is 2.4.5 corollary. And this states that, so if T is greater than 0, then there exists a natural number, say N of T, so that 0 is less than 1 over N of T, which is less than T. Okay, so the proof of this is actually very simple. So proof. So by the previous corollary, we're going to use the previous corollary in this proof. So, so since the infimum of the set of 1 over N, such that N is a natural number, we just showed that that infimum is 0. Right? So since the infimum is 0, T, if it's greater than 0, is not a lower bound on this set. So what does that imply? That implies that there exists some element of this set that's larger than t, right? Because t is greater than 0, and the infimum is 0. So maybe hence there exists some natural number on this, some natural number where 1 over n is greater than that 0, right? And also less than t, because t is no longer, t cannot be a lower bound on that set. So there is a natural number so that one over t, or 0, which is the infimum, is strictly less than 1 over n of t, which is less than t. So as you can see, that's just a straightforward application of the previous corollary together with the definition of the infimum of a set. Okay. So next, let's look at this corollary. So what does this say? It says that if y is greater than 0, there exists some natural number, say n of y, so that ny minus 1 is less than y, or less than or equal to y, which is strictly less than n of y. So any positive real number, there is a natural number that bounds it above and below with the subtraction by 1. Okay, so let's look at the proof of this. So notice that there is some natural number that's larger than y by the first Archimedean property that we proved, 2.4.3. So note 2.4.3 implies the set, I'll call it E of y. And what is this set? It's a set of all natural numbers such that y is less than m. So 2.4.3, if you recall, states that if you pick any positive real number, there's a natural number that's larger than it. So this set of natural numbers larger than y has to be non-empty. Okay. So what do we have? We have a non-empty set of natural numbers. So then the well-ordering property implies that this non-empty set of natural numbers has a least element, a smallest element. So this has a least element. And the well-ordering property was covered in one of the earlier lectures. Every non-empty set of natural numbers has a smallest element. Okay, so with this observation, we have a smallest element, which means that hence, well, actually, not hence yet. Let's go ahead and define the smallest element. Let's give it a name. We'll say n of y. So n sub y is the smallest element in u sub y. So now we can say hence n of y is not an element of this set because that's the, oh, sorry, n of y minus 1 is not an element of this set. Why? Because n sub y is the smallest, least element in that set, e sub y. So if I subtract 1 off of it, then it's no longer in that set. Otherwise, that wasn't the smallest element. So if it's not in that set, it doesn't satisfy this condition, right? Which means that n sub y minus 1 is not greater than y, which means it's less than or equal to y. So like thus, n sub y minus 1 is less than or equal to y. And since n of y is in that set, it's greater than y. And then we're done. Okay. Okay. So 2.4.3 through 2.4.6 are often referred to as the Archimedean properties together. Where the first thing we proved, 2.4.3, that implies all of these other corollaries. Okay. So that will finish our lecture on the Archimedean properties of the real number line. In the next lecture, we will actually, these corollaries imply something very interesting, and I don't think that I should put that in a separate video. These corollaries, these Archimedean properties of R, imply that there's something called density of the rationals in the R, in the real numbers. So as we have seen, and you've probably seen before and we'll see again, the set of irrational numbers is uncountable, right? Whereas the set of rational numbers is countable. So that's just something to note. So the irrational numbers are uncountable. Okay. There is no one-to-one correspondence, no bijection from the irrational numbers to the natural numbers. But the rational numbers are countable. So what does this mean in terms of like the number of these elements? It means that, so what this is saying is that the cardinality of the rationals is strictly less than the cardinality of the irrationals. That's what this is saying. But if you look at a real number line, of course, we have the whole numbers. So forth and so on, right? But if you look in between these numbers, like any whole numbers, you can find like there's like a half, a fourth, eighth, so forth and so on. You can find an infinite number of rational numbers in between any of these whole numbers. So there's a lot of rational numbers, but there's still more irrationals than rationals. So that it seems strange. This is a strange property of the real number line. But what we can say, though, because of these Archimedean properties, whereas a consequence of these Archimedean properties, so I'll say 2.4.3 through 2.4.6 implies something called the density of the rationals. So to imply the rationals are dense in R. What does that mean? It means that if you pick any two real numbers, there's always an irrational number between them. So that arrow should go over here. If you pick any two real numbers or irrational numbers, I'll say real. There is always a rational between them. In fact, there's infinite many rational numbers between any real numbers. So when you hear the term dense in R, that's what this means. So no matter how close together we pick two real numbers, there's always going to be at least one rational number between them. And what's more, there's actually an infinite number of rational numbers between them. So with that being said, we're next going to prove something called the density theorem. Before doing so, I'm going to pause the video again and clean my boards. Okay, we're back and we'll finish this lecture with showing that the rational numbers are dense in R. And we'll do this with what's called the density theorem. What does this state? It says that if X and Y are arbitrary real numbers with x less than y, then there exists a rational number r with x less than r, which is less than y. No matter how close together these real numbers are, there's always going to be a rational number between them. So how are we going to prove this? Well, we'll prove the case when both x and y are positive. The case for negative should be treated separately, but the proof idea is the same. So suppose x is greater than 0 with x less than y. Okay. So if you look at your notes and you look to 2.4.5, so maybe I should write that down somewhere, just so you can recall. So 2.4.5. Hopefully you can read that blue. So what does it say? It says that if t is greater than 0, then there exists some natural number n of t with 0 less than 1 over t, which is less than t. Okay, so that's what 2.4.5 states. Okay. Okay. So by 2.4.5, there exists some natural number, I don't know, n, so that y minus x is greater than 1 over n, which is greater than 0. So why is that the case? So in this theorem here, 2.4.5, so notice that x is strictly less than y, and x is greater than 0. So what this is saying is that, so since 0 is less than x, which is less than y, this implies that y minus x is greater than 0. Okay. Now this is just like, you can think of this as like your t up here. So then this theorem implies that there is some natural number that's such that 1 over that natural number is less than t. That's like your t. So that's where this inequality comes from. Okay, so what does this imply? So this equation here implies that n times y minus n times x is greater than 1, right? And this implies that, what do I want to say? If I just add nx on both sides, I get that ny is greater than 1 plus n times x. Okay, and I'll call this like equation 1 or something. Okay. Now, this is just, so what can we say here? If we focus on nx, we focus on that piece right there, that's just some real number, right? It's just nx is some real number. So by 2.4.6, actually I should write out what 2.4.6 is. So it says that it's, I think, what was it like? Yeah, so if y is greater than 0, then there exists some natural number n sub y with n sub y minus 1, which is less than or equal to y, which is less than n sub y. So we focus on that number, right, which is greater than 0, by the way, because x is greater than 0 and n is a natural number. We have maybe some natural number m. So that we have that m minus 1 is less than or equal to nx, which is less than n. So it's just squeezing that real number in between those two natural numbers. So maybe n so nx is less than m, right? Nx right here is less than n, but it's also greater than or equal to n minus 1. Okay, so this term here, right there, that is greater than or equal to n minus 1, right? So that means that ny is greater than nx plus 1, which is greater than or equal to, oh, sorry. That right there, that single term right there is greater than n minus 1. So if I replace that term, I get that ny is greater than 1 plus n minus 1. Okay, so that's what I'm going to write here. Nx is less than m, which is less than ny. Okay. So here, if I replace that by n minus 1, the 1 and the negative 1 go away, so I get that is strictly greater than m. Right? So ny is strictly greater than m, and m is strictly greater than x, right here. So now dividing both sides by n, we get that x is strictly less than m over n, which is strictly less than y. Where M over N is a ratio of integers with non-zero denominator, so that's a rational number. So that shows that we're able to find a rational number that is squeezed in between x and y, where x and y are any real numbers. And it's a consequence of applying these Archimedean properties of the real number line, which all come from the completeness property and supremums and infimums. All these definitions are starting to build up a lot of the fundamental aspects of the real number line that you took for granted when you took a course like calculus. So that's what real analysis is doing. It's the theory behind calculus. It's the rigorous built up building blocks of calculus. Okay. So that will be it for today's lecture. Stay safe.